and welcome back to the last session, I guess. Last week, sorry. First session, sorry. Okay, so the first talk will be given by Gabriele. He's from ETH, and he's going to give lectures on hydrodynamics. So over to Gabriele.
Thank you very much. Thank you very much for the introduction. Thank you for inviting me. It's my first time here in Mumbai. And I will give you today and in the next few days this series of 4 lectures which revolve around this topic here, which is hydrodynamics in general for a particular class of systems which displays interesting behavior, which are integrable models. And it will be presented in a way which is both classical, valid both for classical and quantum systems. Before going into the details, just at the level of organization, I think all the lectures will be Blackboard with the calculations on the Blackboard. So we will derive, I think, 90+% of the calculations at the Blackboard. I will not assume, in the title, for instance, you see there is integrable systems. I will not assume any previous knowledge of any kind of integrability. So if you don't know it, don't worry. We will introduce the most basic concepts that we need along the way. I will just assume basic knowledge about statistical mechanics like ensembles and so on. This is the main points. Then all the lectures will be Blackboard with calculations. Apart just, I have 3 slides now as an introduction, appetizer. And there will be exercises. I will share with you, I think, already at the end of today's first lecture. I have an exercise sheet with 3 or 4 exercises to practice a bit with the concepts that I will introduce along the way. And you are free to take all them as much as you want, as much as you are interested in. And then we discuss them together in the tutorial lectures, I think today and maybe Friday, yes. That's it. And needless to say, you can stop me anytime for questions. Okay. Apart from this, then we start with the appetizer. And let's say what we discuss about are non-equilibrium processes. Non-equilibrium processes, in a broad sense, without technical details, can be, let's say, embodied with a river that flows. And in a river that flows, there is transport of matter, energy, particles, whatever, in a certain direction, for example. And every current and flow is usually comes together with the breaking of time reversal symmetry, because you have a specified direction for this river to move. And if you watch it in the backward direction, you will see something different. This is different, for example, from the case of a lake. In a lake, water is still, and therefore you can watch the dynamics of a lake backward in time or forward, and you will see the same stuff, just loosely speaking. So lake is like equilibrium, and a river is a non-equilibrium process, dynamics. And here I'm citing from this book, this will be also one of the main references, especially I think for the first lecture will be the main reference, this book here from Spohn, that was was talking about the river Isar, which flows through Munich in Germany, south of Germany. And the question is that he was asking is like, if you were in principle able, like Superman or something, to resolve at a nanoscopic nanoscale the motion of each particle of water in the river, you will see something like erratic, moving in a pseudo-random way. But surprisingly enough, when you zoom out your description and you look at the river as a macroscopic system, the way we do, where we typically observe phenomena at the scale of, for instance, lengths of order 1 meter, you will see something that is pretty much deterministic, specified the flow, which depends only on few macroscopic properties, like the velocity of the river will depend on the temperature of the environment, the pressure of the river. There will be some equation of state, simple enough in terms of few parameters, not 10 to the 23 or whatever for the number of particles, which dictates the dynamics of this system. So in a sense, when you pass from the microscopic scale here on the left, where you resolve each individual atom, to the macroscopic one, the one that we experience and we measure, okay, you will see that there is a step, a flow towards some large-scale organization of the system into something well-defined, some kind of equation of motions, which, for instance, for a river, for hydrodynamics, what we are interested in will have the form of Euler or Navier-Stokes kind of equations that you have probably met. And the central question that we ask, this is central in statistical physics, but I would say in all branches of physics, treated in possibly different way, is how is it possible to pass from what is at the beginning purely microscopic and in principle dictated by reversible law of equation, like something like Newton, to a macroscopic effective evolution equation in terms of few emergent degrees of freedom. I can also use hands, don't worry. I am Italian, I am used to this. And then, of course, disclaimer, this is a huge elephant to catch, a huge tiger, since we are in Asia. There is no general answer about this is a question which is as large as central physics, but at least I will provide some ordering principles for these questions in some specified setups, which are the ones where you have a system which is weakly homogeneous, weakly evolving in space and time, and can be described by hydrodynamics. Then, a last question of appetizer. This is all about classical system. Now I want to introduce some quantumness, because in the school, the title, there is also quantum, so at the end we want also to see something quantum, right? I will cite this example. This is not a river. This is like, imagine you have a river, but now you cool down the river to very low temperatures, so that you will see something strange. You see quantum mechanical effects becoming relevant and important. And this is what is known as a cold atomic gas. Here I'm studying from one paper where they study a specific gas, which is a gas of rubidium-87 atoms. And the gas is at the beginning, this is confined in a certain trap, which can be harmonic or non-harmonic. This is not important at the end. And by laser draving, essentially in the experiment, they will transfer some momentum to this atomic cloud. This is called Bragg pulses with laser, so that the atomic cloud will split into two counter-propagating subparts, let's say. And what you see essentially is that you can imagine that it's like the Newton cradle, which is this toy object that we have seen, I think, sometime in the life, where you can move up one bead, and then this will start moving, will collide with the other particles, and this will generate this kind of oscillations back and forth. And here, surprisingly, what is found is that when you have these two counter-separating subparts, they will undergo, of course, oscillations inside the potential, because at some point they will come back because they are confined, and they will collide, for instance, here. And after collision, there will be a lot of interactions between the two parts, and then you will see that there are two parts which emerge from the collision again and start propagating. And importantly, what is observed is that within the time scales observed in the experiments, which are here expressed in milliseconds, you see this is an absorption image, so the red spots can be thought as density of atoms. Horizontal axis is space, vertical is time. And you will see that you have exactly something like this. They collide, and then they separate, and this goes on in time as you go below. And importantly, within the time scale observed, there is apparently no damping effect. These oscillations in this motion, complicate motion of this cloud of atomic gas goes on and on without damping, which is what you would expect, because maybe in principle when they meet, they dissipate some energy, and then at some point this stops. It's like the cradle after a while, because of friction, viscosity, and everything stops. Here within the experiment, this was not observed, at least within the scales that are observed before the coherence effect comes in and all the story. Okay, and here this is copied and pasted from part of the paper. They were saying, this is also to introduce the other keyword of the title, which was an integrable system. They say that the results are probably explainable in the fact that the Bose gas, which is what theoretically describes this kind of system, don't worry, we will write equations for all this stuff. So at the moment I am purely qualitative, but then we will go deeper. So the Bose gas can be thought to be an integrable model. However, they say that the dynamics is an unsettled issue, because of course describing this kind of system is complicated, because you have a lot of atoms, quantum mechanical effects, low temperature. This is like the river that we discussed, that we saw before qualitatively. It's a system composed of many in the macroscopic agents interacting and giving rise to something at the macroscopic scale complicated. So it's not easy to discuss, unsettled issue. And they say in particular at the practical level, possible difficulties arise from the fact that the cold atoms are trapped by a potential, and this potential breaks translation invariance, and these plus interactions, and this can make the theoretical and in general the understanding of this kind of dynamics complicate to achieve, okay? And what we will see is that this can be, to a large extent, very well understood using hydrodynamical methods, okay? So in a way unified with the picture of the river, but this is a sort of quantum river because it has some peculiar features, and in particular integrability. We will discuss this, and keep in mind this picture because we will come back at the last lecture about it. And with this, I think I am done for the appetizer, and I think we can skip to the blackboard. Do you have questions so far? These I just switch it off. Yeah, rest of the lectures from now on will be essentially on the blackboard. We do calculations together, plus, as I told you, there are exercises. Some of them require some numerical solution of the kind of equations we are going to write, so we will do together in the tutorial, and I can share also the screen to show live the kind of solution and that we get. Okay, so now let's see if I understand this. Understood. Okay, so I will write like one of my favorite professors was always doing in the lectures. The first lecture was the schedule of the course. This was taking something like 30 minutes. We do it fast. So. Gambassi first lecture was 2 hours, 1 hour, just writing the schedule of the course. But the course was good. I hope I can achieve similar levels. Okay, I'll try to polish my handwriting, which is very poor. If you don't understand any symbol, tell me anytime, okay? So schedule of the course, we have 4 lectures. So lecture number 1, it's about hydrodynamics, in particular the general structure of the Euler hydrodynamic equations, which are the one that we will study. Okay, this is lecture 1, essentially what we do today, hopefully. Is this understandable, written in this way? Okay, okay, I will try to write this because otherwise it gets horrible, my writing. Then second lecture, which I think is already today afternoon. So in the title there was integrable system, so in the second lecture we discuss more integrable models, basic aspects, integrable models. And in particular their thermodynamic description. And here there is one keyword appearing, which is this one. Which is thermodynamic Bethe-Ansatz, which I will show is in a very effective way to describe the thermodynamics of this kind of systems, integrable models, TBA, which will be the acronym henceforth for thermodynamic Bethe-Ansatz. It's not to be assigned. And then these are the first 2 lectures, so we will probably cover everything here today, between today morning and today afternoon. Then third lecture is essentially 1 plus 2, so we will merge these 2 concepts. So we will take the hydrodynamics and the formalism for integrable models, and we will write hydrodynamic equations for integrable systems. Integrable. This will be called and essentially the hydrodynamics of integrable systems will take this name, which is generalized hydrodynamics. The short is GHD. I think I will just introduce these two and another one which come later. Don't have to remember too many. And then section lecture 4, so the last one, will be about, here we have settled up all the formalism, some applications to get ideas. In particular, how to solve the equations. Then some kind of examples. One is called partitioning protocol. We will define it later. Protocol. And then external force field. Cold gases. So external force field is like hydrodynamics in the presence of an external potential, like before where we had this confining potential. And one example is the one of cold atomic gases that we saw on the slide. We will try to discuss that. Okay. And yes, I think this is the whole structure. And as I told you, there are plus tutorial. Tutorials, because maybe there will be some more in the afternoon, 1 or 1.5. In the tutorials, we discuss together exercises, okay? I will share, I think at the end, I have a LaTeX with an exercise. At the end of this lecture, I will share it with you, okay? And that's it. Voila. No.
So the example that you showed, this collection of bosons in a trap. So, if you study the out of equilibrium dynamics, then the integrability can be sacrificed even if there are no interactions?
This is a good question. Indeed, when you apply the potential, it's not integrable anymore, that model. But if the potential is slowly changing in space, you can still use integrability to describe. This is the good point of this method, which is somehow robust with respect to integrability breaking terms, and this still sacrificing integrability, you can describe it. We will discuss it. Yeah, that's a good point. Okay, then we start with point 1, so hydrodynamics. This is an I, in particular Euler. Euler, we will specify before. Here I will start writing what we know, probably from school, which are Euler equations. And these are equations for conservation laws, which characterize a fluid. So the first equation is like conservation of mass. So you have this is a rho, so it's a density. So this is the density of particles in space, and this is the velocity at which the fluid moves, okay? Then we have the equation for the velocity. this is the equation for the velocity. This guy here is usually called the convective derivative when you read books about hydrodynamics. This is the density, rho. This capital P is the pressure of the gas, which depends on the density and the energy, mass density and energy density of the gas through certain equation of state, which is a model-dependent bit of information, okay? So equation of state tells you how the pressure relates to the macroscopic observables like density and energy density.
Sorry, what are the arguments in the question?
This is a rho. This is an E, that energy density, and now we write the equation for it. Yeah, it was not yet defined, indeed. The entity is E, so this is a lowercase e, it's the same here. Okay, so this is mass conservation. This is momentum conservation. And this is energy conservation. Okay, so these are the three kind of Euler equations that you find in book that describes the dynamics of a fluid. An unviscous fluid, because here we are dropping a viscosity term, which usually appears here on the right-hand side, and this is why I call these equations Euler. Okay, and just as an additional step, I want just to show you, for instance, if we consider these first two equations here, we can write them in a slightly, no. Very good.
Sorry, I joined late. So
Sure.
That is rho, and what is the other one? What are the arguments of?
Yes, this is a rho. Let's say I write it.
Because I see several rows.
Maybe they all look similar. This is mass density. Then the one, let's say I do it with two, so that it's different. This calligraphic, this is a P, and this pressure. Okay, and E is the energy density.
And P you take as a function of rho, and what is?
This is rho, and E, which is the energy density. Okay, and these are all functions of space, x, and time coordinate. Here I have written it in one dimension, just for simplicity. Of course, you can write also in generic dimensions. Okay, then I want just to show that if you take the first two equations, we can write them in a slightly more appealing form, which is like we define J, which is like V times rho. This is like the current of mass, okay, because it's like the mass density times the velocity of the fluid. And then we can define this object here. Let me be consistent with the writing. This K, which is pressure plus density V squared, velocity squared. So this is like a current, but of momentum. And if you use these two definitions, okay, you can see that these two equations here can be equivalently rewritten, same stuff.
The third equation there, del E of E plus.
What? Which one?
The third equation, energy conservation.
Mm-hmm.
Del T of E plus del X of
Velocity times.
VE.
This is velocity, which multiplies energy density plus pressure.
Okay, so that's why you define it as a current.
Exactly. And you see that if you use these two definitions here, the first two equations, so like mass and momentum, take this form here. And this form is particularly appealing because what is reminding you, this is like the form of a continuity equation in physics, right? So where you have time derivative of a density equal to minus divergence, which in one dimension is derivative of the associated current, okay? So this is like, these are continuity equations.
The second equation says that the time derivative of the current is the negative of the divergence of the...
What?
The second equation says that the time derivative of the current...
This is time derivative of the momentum density is equal to minus the divergence of the momentum current, which is this.
You call it the K, you call it momentum current.
Yes, yeah, I write it. Density. Voila. So, for instance, you have these two. And this immediately shows that Euler equations have the meaning of conservation laws. Continuity equations are universally in physics associated to conservation laws. This is conservation of the mass of the fluid. This is conservation of momentum. Okay. Then just want to add some remarks that probably we have not seen. First of all, for instance, let's say I number them. Okay. In this equation, for instance, which is the one for momentum, we could also include the effect of an external potential. For instance, for a fluid, an external potential could be gravity, because the flows takes place in the presence of a gravitational field. Of course, the presence of a gravitational field breaks momentum conservation, okay? So this will have some effect on the large-scale equation for momentum, okay? In particular, if you include an external potential, you see that here you should include an additional bit, which is something like minus derivative of the potential divided by the density. I write it like this. It's like here, if you have an external potential, this is like the gradient of the potential. So it's like the force field, okay, associated to a conservative field divided by the mass density. For instance, you could say this is the effect of an external potential. This will be useful because this is to go in the direction, for instance, of the example that we saw on the slides about this cold atomic cloud, which was set in the presence of a trapping potential. So it's like something like this. Okay. And then also an important point is that these are Euler equations. They are unviscous, so they describe unviscous fluids. Usually in hydrodynamics, you also find Navier-Stokes equations. Here in Navier-Stokes equation, you have in addition here some term which depends on the viscosity. And the viscosity and also the second derivative of the velocity. I will not discuss this case here, but just to mention that this is usually account with diffusion because it changes the scaling of the motion at large scales and comes from viscosity. Okay, it contains a lot of physics, but I don't think we will have time for that. This is already enough for what we want to say.
So Gabriele, just one thing, just trying to remind myself of my kindergarten days. So I used to, there was this Bernoulli's principle. So that follows from there, right? I put del T rho equal to Bernoulli's equation, conservation. How do I recover from those continuity equations? I put del T rho and...
Bernoulli. Yeah, I think it was following, I think it's also related to this because it's like a conservation law.
That one becomes a constant.
This becomes a constant and that becomes a Bernoulli equation. I think.
Then I should put del T rho equal to 0.
I think to get Bernoulli, you also put a gravitational field and then you look for stationary solutions, if I remember well.
Solutions of that, okay.
But you see, this is exactly the kind of integral of motion that you have in Bernoulli stuff. Okay. And okay, then at the level of physics, you see that this is already being able to write some kind of equations like this is highly non-trivial and is already a huge result for a physicist, because you see that there is a huge reduction in the number of degrees of freedom. Oh, yeah.
In presence of the field, doesn't the K will modify? In presence of the field, won't the K term modify?
Also this one modifies. I think there is an effect also here, yeah, which I have not written. The mass is the same, because the...
K also will modify.
Yeah. The mass not, because even if you add an external field, the mass is still conserved. Momentum not, and indeed there is an extra term in the equation. So the fundamental principle behind principle. Okay, it's the reduction this is degrees of freedom, okay, DOF. So because you see that you start from a dynamics which describes a large number of particles, so in principle Avogadro number, 10 to the 23, so you would need, I don't know, 10 to the 23 times 2, so for velocity and momentum of each particle, so a large number of microscopic variables, but at large scales what you see is that you can describe it in terms of only 3, because it's raw, velocity, and energy density. So you pass from 10 to the 23 to 3, which is a lot of stuff. And this is a reduction of the number of degrees of freedom. And it relies, as we see, on the separation of space-time scales. Separation. In particular, if we want to see it in a essentially when you stay at a purely microscopic level, so you resolve very fine distances, here you see microscopic trajectories. Okay. If you start then zooming out, so what we typically do in statistical physics, so you increase the space-time scale at which you observe the system. For instance, a favorite argument of Boltzmann, so you pass from individual particles, you start coarse-graining the phase space, and you can define a density in phase space, right? Number of particles with a certain velocity and momentum. And this gives, when you increase a bit, the scale to Boltzmann equation. For phase space density. And then, after a while, you see that in the Boltzmann equation, typically you have somehow some collision term. These collisions tend to drive the system towards a relaxation, right? It's Boltzmann edge theorem. And we'll describe relaxation to some state which has a maximal entropy state, okay? Before you reach the very long time, this maximal entropy state can still encode modulations in space and time, and this is exactly where hydrodynamics kicks in. Euler. Okay. And if you wait long enough, again, then at the end, the system will eventually will reach a thermal state, right? Will become completely homogeneous, stationary, and will be described by some thermal state, Boltzmann-Gibbs, and therefore by thermodynamics. Okay.
Between these two.
And here, in the course, we are here. Yeah, please. Yeah, please go.
Between Boltzmann and Euler, this is the regime where you assume local equilibrium.
Exactly, here. Exactly, here.
Between these two.
Yeah, this is local equilibrium, is what local relaxation, maximal entropy.
Okay. So that's fine. So locally you equilibrate, and then these end of patches would eventually
Merge into a single homogeneous, which is thermodynamics.
And the first loss of information is when you go from microscopic to Boltzmann.
It's here.
Yes.
Here there is a huge chunk of physics, because when you define this phase space density, you coarse grain, so you lose information, and this loss of information is usually what brings you from a microscopic reversible dynamics to something which is already irreversible, which is Boltzmann. Yes. Do you have questions? Okay, if not, then let's see. Since this is where we are, this is like the map, we are here, so in the course we are here. Since you see that hydrodynamics is based on maximal entropy local relaxation to some thermodynamic state, so I will start discussing and remembering some basic aspect of thermodynamics. Okay, so for thermodynamics, let's see if I can do no. So for thermodynamics, for instance, let's say in thermodynamics, what we want to describe is a macroscopic behavior of a system. So we want to describe some observable, which could be everything, could be magnetization, pressure, velocity of the gas, whatever, some observable, macroscopic, and we want to compute its expectation value, which is the bracket notation, over some state, which is labeled by a set of temperatures, okay? So this is like the beta is the inverse temperature, something like this. Okay, where this is, for instance, this is the Boltzmann-Gibbs form, is exponential. These Q are conservation laws. Here I'm writing in the case where there are multiple of them, but for instance, let's say in the case of the gas that is there, for example, one could have that Q naught is equal to the number of particles. This is one conservation law for the total number of particles that you have in your system, which I label with the subscript 0. Then we have momentum. This is a P, it's momentum. This is like the momentum of the gas, because it sums the momenta of all the particles in your gas. And then you have energy, of course. This is, for instance, is the energy. Can you see it also in the bottom? Maybe. This is like the energy of the gas. You see, this is kinetic energy, and this is potential energy of interaction, for instance, for two-body interactions. These, for instance, are the three conservation laws that describe a classical fluid and boils down at the end to those equations. And these are thermodynamics averages over the associated Boltzmann-Gibbs distribution. The beta are the inverse temperatures. Here I'm using this trace notation, which reminds quantum mechanics, but actually, I mean, let's say the mathematicians will say that you can replace the trace with the average over any flat measure over the phase space in the classical case. So something like integral dx dp, and then this also in classical statistical mechanics. This is why I say that what we discuss translates one-to-one from classical to quantum. And yeah, and that's it. And these are the conservation laws.
So betas are not necessarily the inverse temperature. It depends on the quantity, right?
Yeah, exactly. Beta, to each conservation law, there is an associated multiplier, beta. For instance, the one associated to the Hamiltonian, it's the inverse temperature, 1 over the T. The one associated to n can be understood as chemical potential, and this one can be associated to a velocity, okay, because it's coupled, conjugated to momentum. And no. No, the other way. Ah, the left. No. Ah. Maybe at the end of the lecture I understand this. Then, to each conservation law, you can associate like a density, right? Something which is local in space. This is an I. This is like charge density. For instance, to these three, you can write the associated density that you can verify directly, or something like that. Okay, so these are like densities, which you see they have a clear interpretation. This is for these are the delta function. So this, for instance, counts the density of particles on a given observation point x. Clear? You see that if you do the integral in space of this object, you trivially get this one. No big surprise. The same also for this is momentum density, because it counts at every point in space if you have a particle, the associated momentum, and this is the same for the energy. So here I'm using the labeling where 0 is the number, 1 is the momentum, and 2 is the energy charge, okay? It's conventional, we will follow this, okay? So now, with this, another comment I want to make first, before passing. You see, in this kind of writing, Boltzmann-Gibbs measure is usually understood as an equilibrium measure, okay? But in general, you see that in the exponential, there can appear conservation laws, like the momentum, which are odd under time reversal. Momentum is clearly odd, right? Because momentum describes flow. So if you do time reversal transformation, a velocity is odd, so it changes, okay? So it's like the river, what we had in the first slide. If you watch it backward, you will see a flow in the opposite direction. So in principle, a state like that, when in the exponential are included charges which are odd under time reversal invariance, breaks what is called the detail balance, microscopic reversibility, and therefore is a non-equilibrium state. It describes some large-scale flow, supports flow of a current, okay? In particular, if you have this multiplier, this P, this describes some current, for instance.
Can you again explain this last
The, what I was saying in words, I'm saying that here in this exponential you have multiple charges appearing. In particular, some of these charges, let's say here we have 3, behave differently under time reversal transformation. Hamiltonian and number of particles are even under time reversal, of course. Hamiltonian evolution is reversible and number of particles it is as well, but momentum is odd, because if you do a time reversal, the P goes into minus P. And therefore, this state here is not invariant under time reversal, as soon as in the exponential you have this object here. And since it breaks time reversal symmetry, it's a non-equilibrium state. Time reversal is what we usually associate always to equilibrium in stat-mech. So just to say that Boltzmann-Gibbs states are not necessarily always equilibrium form. And yes. Yeah, exactly. I just want to say where this object comes from. This comes from the Boltzmann-Gibbs entropy maximization. Maybe I want to write it.
Momentum conservation, which is breaking the time.
This I should not use it, right? Then I go back here.
Or you can go up. No?
There is again.
One thing repeats itself.
And when I go, it cleans automatically. No, I have to clean myself already.
At some point, you can.
No, I don't know.
You're expecting too much.
Yeah, exactly. No, I mean, you are rising expectations. I mean, okay. And I say Boltzmann-Gibbs is every measure that has the form of exponential of minus some multipliers times conservation law, something like this. This is like what you call Boltzmann distribution. Okay. And where does this come from? I just want to remember is from entropy maximization principle.
So, Gabriele, just a quick question.
Sure.
This momentum conservation, what is breaking the detail balance condition, I can always go to a co-moving frame and then it's fine, right?
Yeah, exactly. For a classical fluid, let's say yes. If you move to some frame, then you can drop it. In integrable models, you will see that there are multiple of them that breaks these, and therefore this stuff doesn't.
So you need at least 2 to break.
I think so. Yes.
Because one I can always do some transformation.
Yes. And where does this structure, this exponential with conservation laws, comes from? Yeah. Sure.
When you compute this trace of a classical observable, so then
Trace is like integral over phase space.
right, so it's ensemble average. So when you do that, do you assume this phase-space density to be uniform or some spatial density?
Here there is no space still. It's uniform. Everything is uniform. It's thermodynamics. So in the picture that we had with the scale, it's the largest scale where everything has already homogenized. And so
measure dx will be the same there as well, right? So integration dx and the same that will be calculated in the same way that you do for the charge for the concept.
So you say that the average of these over a state like that will have no space dependence. This is my statement.
Okay.
And just to say, where does this come from? From the entropy maximization principle, where you define this object here. This is an S. This is like for quantum systems is von Neumann entropy.
I think O is the force grain variable. So O is the force grain variable. So after you have done this.
So von Neumann entropy, and then maximal entropy principle means that you want to maximize this object with respect to the state, so it's a functional maximization, given the constraint given by all the available conservation laws. So you do variational derivative, functional derivative. if you do, for instance, the functional derivative of this object here, you will see that, and you set it to 0, you see that you get something like that, where this is an alpha, it's a multiplier which is enforced, encoded in the calculation to enforce normalization of the row, of the state, trace of row equal to 1, or distribution normalized to 1. And from this, you see that if you solve it, you get exactly here, with multiple conservation laws. So for instance, yeah, the trick is always when you write this equation to put first the left, the right, and then write the equal, because otherwise the equal is not aligned with the fraction. I got this criticism many times from my supervisor, but still. If you solve this, you get this stuff, and this is exactly, for instance, the grand canonical measure that we use, for instance, there, associated to those 3 conservation laws. So this is like maximal entropy principle. Yeah, please, please. Alpha here, this one is a multiplier, because it's a constrained maximization. It's introduced because you want to enforce the constraint that the trace of rho is equal to 1, normalized. It's essentially, it's what gives back then the normalization, the Z. Okay. Okay, so this is everything that we need from thermodynamics. And now, let me... Okay, so now we want to pass from thermodynamics to hydrodynamics, so we want to introduce space-time variations. This is completely homogeneous, right? So Euler hydrodynamics. So, from inhomogeneous and non-stationary states. So we want to describe now something which changes as a function of space, inhomogeneous, and time, non-stationary. This is like what we expect, right? Hydrodynamics is like the flow of a river, so there is something which is modulated in space. So we want to go beyond that description. And, but still, we want to stay at a large enough space-time scale, as we sketched before, so that we can assume that locally we still have maximal entropy. So in particular, the main assumption here will be local entropy maximization. So if we take a generic observable O, local, let's say, this is like observable or local at some point in space x and time t, and the average here, the bracket, is taken with respect to some state, let's say rho, which is some complicated state because it changes as a function of space and time, it has modulations. It's not macroscopically any kind of Boltzmann-Gibbs measure. It's something complicated to treat. So this object is in general hard to compute. It's essentially a solution of a many-body problem. But if we assume this local entropy maximization, we can say that this is essentially equal to the average of the same observable over now a state which is of maximal entropy form. This under bar underscore notation means it's a vector of multiplier because you can have possibly many of them, evaluated on the space-time point on the what is called the fluid cell where the observable sits, okay? And here now I have shifted to 0 because this average over this max entropy state, this state is homogeneous and stationary, so I can use space-time translation invariance to shift the point from xt to 0, 0. But space-time translation invariant of this state here, the max entropy, not the one that was originally here. This is a big chunk of assumption, and actually, so what was the question?
This equivalence thing.
What were, sorry?
This equivalence, how you are writing this.
Mm-hmm.
Can you repeat again this?
Yeah, now I will make it more precise. I will this is the central point. I understand that it requires time to digest. This essentially requires, when is this valid, to make it more, let's say, solid, and what is the meaning of that, and how this equivalence is observed. Let's say we have this state here, rho. We take it to something which is inhomogeneous and non-stationary, but evolving on large space-time scales, so slowly. So we take for this something like, I put a subscript here, which I now introduce. So I introduce here, I put a length scale, this lowercase l, and I write a state. Let's say this is an example which is very useful for illustration purposes, which you see this state here has multipliers, these inverse temperature, generalized inverse temperatures, which depends on space. You see they are function of the space coordinate, so they are not homogeneous as in that case above, over there. They depend on space, but they depend, let's say, weakly, because the space coordinate is scaled by this parameter, this length scale here, L, so that this state here will have variations which occur over a macroscopic scale, so this changes when y is of order, let's say, L, okay? To observe variation over such a inhomogeneous state, you should look at space scales which are as large as the scale parameter L. So if this scale parameter is large enough, this is a state which is weakly changing in space-time. So let's say something like, I'm getting there. Let me do it like that. The question was, is this an answer? I mean, this is a choice for illustration purposes, let's say, because I take this because this has the form of a inhomogeneous state, but point-wise on each point, point by point, if you look at that, has the form of a maximal entropy state. So it's something which describes local relaxation. In principle, you can start also from a state at the initial time, which is not of this form, which is complicated. You write it whatever you want, but if it is slowly varying at sufficiently long space-time scales, according to the local maximal entropy principle, will take this form here, okay? So I say it's not restrictive. The important point is that for this to be valid is that you have to describe weakly inhomogeneous and non-stationary states. So you have to observe, to be interested in a setup where you have a weak space-time inhomogeneities. This is the regime where hydrodynamics applies and where this local maximal entropy works, okay? And yes, so if you take this, which therefore shows very slow variation over a scale L, then the more precise form of this equation here is that. Yes, I'm coming. Yeah, this is like the initial time. Then now when you evolve, you have to scale both. This is the statement, more precise. This is the more refined version of this. So you take this scale parameter L, which is here, and then you look at observables evaluated as space-time rescaled points, so scaled according to this macroscopic scale parameter L, so that you look at long enough times if you start increasing L and large space-time scales. So you look at, it's like when the river, you have the molecules at microscopic scale, but then you start zooming out more, and increasing the length scale. And if the state is slowly varying on that scale, you see that computing, if you're interested in finding something on this macroscopic space-time point x and t, you can essentially disregard the whole structure of this complicated inhomogeneous and non-stationary state and evaluate this simply by averaging over the local maximal entropy state evaluated on the space-time point xt. This is the statement of local maximal entropy principle, which is at the root of Euler hydrodynamics.
I have a question. So,
Of course, yeah, it's not all trivial.
you have to consider two limits, right? One is that your thermodynamic limit is the system size going to infinity.
This is assumed to be already taken, yes.
Okay, so these two limits doesn't necessarily commute in your equations?
No, first you take a thermodynamic limit, let's say.
You push the L to infinity and then you take
This L is not the system size.
No, I understand. But I mean, you are already considering a thermodynamic system.
Yeah, macroscopically large system.
But the small L can go to infinity, but then small L by capital L should be some finite number, right? This one is infinite and this one, both can...
I think they grow together. In principle, I think you take first the thermodynamic limit.
And then this one...
You look at local observables embedded in a macroscopically large system, okay? So that you don't see boundary effects. Otherwise,
Say both can grow together. So I first take the limit capital L going to infinity.
capital L, you mean thermodynamic limit, size. And then you start looking at length scales, which are larger and larger on a macroscopically large system. I don't have to go here, but maybe I can use this.
So basically, that is, yield is the length scale on which I have a local equilibrium, right?
It's the length scale which characterizes spatial modulations over your state. Then the point is that there is even a more refined version of this, but I want maybe to write it, let's say, you have your system. This is a space coordinate, let's say, space. And you have some modulation in space-time, which is law of the Lagrange multipliers. So let's say this happens over a length scale, which is L. This one here, okay? And you want to look, for instance, at an observable on some property, for instance, here, on this point. And let's say if you look at here, for instance, you can take what is called a fluid cell. So you can take an average over a region which has a length scale, let's call it capital L, okay? Which is, this capital L is still large to be able to contain multiple particles inside. So imagine here there are many particles. It's still large to be thermodynamically large, but much smaller than this. So that here, locally, you see something that is still homogeneous. You don't appreciate the space variation. And here you contain a lot of particles, but you are scaling this length scale here to very large values. So essentially here you forget the microscopic details of all the particles that are inside, and you see a continuum, a fluid. This is the interpretation. So you look at observables, local. Local is like on a specific point, but you could include some averaging over what is called this region, capital L is called the fluid cell. It's like a patch of your system, which is large enough for thermal equilibrium to be attained locally, but smaller than the macroscopic scale so that it looks locally homogeneous. And in that regime, this can be described, it becomes a continuum because you don't look anymore at the structure of all the individual particles and you have local maximal entropy state.
Right. So I was asking, like, so if L tends to infinite, that means to see any fluctuation, I need to go to like infinite system size, right?
If?
Infinite system.
No, but what are you sending to
I said,
infinity?
like, if L tends to infinite.
The lowercase, this one.
Lowercase.
Yeah, but you also scale up this guy here.
Right. So I was
Otherwise, the limit is trivial.
isn't in that case my beta will be constant, like it will not depend on space and time? because
Y-
like the
y-
to see fluctuation of the
Yeah, the point is that if you don't scale here, you send L to infinity, this just becomes an homogeneous state. So you don't see anything at the level of space modulation. This is why you have simultaneously to scale the space-time point, so that when this increases, you also observe, you compute this at a space-time coordinate, which is following the macroscopic scale, and you see variations. Otherwise, the limit is trivial. I think this is the point.
I have another question.
Of course.
Can you go from local entropy maximization to the global one, the Boltzmann method? I mean, is there a way to see?
So you say from local maximal entropy to this one?
Yes.
This is a very good question. In principle, when you have this local maximal entropy principle, as we will see, this gives rise to Euler hydrodynamics in viscous. To get back the full maximal entropy for the full homogeneous state, at some later time, you have also to include the effect of viscosity, which enters in the viscous term of the Navier-Stokes, and this essentially produces, increases the entropy till you reach the maximal one, which is the Boltzmann state. This is a very good question. How you pass from local entropy maximization to the eventual maximal entropy for the whole state.
So Gabriele, coming back to the same question, capital L, I mean the whole system size is infinite, having the thermodynamic limit. But this small l, when I take the limit small l going to infinity, don't I have to ensure that small l by capital L still remains much smaller than 1? Because
I'm not sure.
Huh?
I'm not sure. If you take a finite size system, for instance, if you keep capital L, what you call capital L finite, at some point you're going to have boundary effects because
No, capital L is infinite. My system.
Yes. Then you send capital L to infinity first, and then L, is grows but is smaller than the size.
So then, when I take the small l to infinity, I have to still ensure that small l by capital L remains.
I think this is ensured by the fact that the order of the limit matters, and first you always take the thermodynamic one. Okay, good. There are other. This is a good. Please.
So you said that if I start from a locally maximized test case, so if I choose a beta whose scales this small l depends on the spatial variation of that beta, but its time variation, because the state is highly inhomogeneous and non-stationary, this time scale will be much different than small l in general, right? The time scale of relaxation.
Time scale of relaxation to what? To the
To a maximum, to the Boltzmann distribution.
to the global one, for the global one. Yeah, that's a big question. It depends on a lot of stuff. I think you have to include also viscosity. I think the scale is larger than the calligraphic L, probably, yes. Because you need diffusion, and diffusion enters in at longer times, because the dynamical exponent of diffusion is 1/2 instead of 1. But I mean, you have to wait longer than the calligraphic L, I think. I have to think.
Sorry if it's a stupid question.
No, it's not stupid, don't worry.
For to maximize local entropy, how do we do that? I know that one it's for the whole system. For locally to do that?
It's like, it's that stuff over there, but on the state rho, you attach xt. So you do it on a space-time point specific. And then the calculation follows the same. You get still an exponential of minus charges, but on the specific space-time point you consider. This is like this local maximal entropy maximization. This is also like local density approximation, but propagated forward in time. It's like bringing the local density approximation to a dynamical level. Because in local density approximation, you approximate your state with a thermodynamic state on each point. And here you are also adding on top of this time. And therefore you say that when you propagate in time, still you remain in this point-wise Gibbs state at the point xt. Does this reply to the answer, to the question? Yes. Okay. Okay.
Gabriele, just a remark. So, like, is it a general principle that as soon as you include some irreversible terms, then things start to smoothen out? Let's say from microscopic to Boltzmann, I included collision, so density became more smooth than what was at the micro level. Then when I go from Euler to this global maximization, you said we have to include the viscous term, which is again a dissipative thing. So then there is a further smoothening out. Like,
Yes, 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 yes,
kind
yes.
of more or less a general principle.
I think as far as you avoid, I don't know, cases which enforce, I don't know, localization or something like that. Of course, I'm keeping aside these cases which avoid thermalization, like localization, or in quantum systems, I don't know, scarce or similar. You can find exceptions, of course. Okay. And then I think once this is the big, needless to say, the statement that I write here in an innocent way, proving mathematically is very hard. And apart from the free gas, so ideal gas, this has been proven only for hard rod model, which we introduced before and was proved in the 60s or 70s by mathematicians. And it's hard rod is the only interacting gas where this statement can be made mathematically rigorous. And I think there is in the book of Spohn, chapter 2 and 3, there is an extended discussion of this. Just to say I'm writing it, but of course this is a huge chunk of physics, this kind of approximation. It's natural that you have a lot of questions and you wonder a lot about it, I would say. Okay, then once we take this, let's say we go back to continuity equations. I still have 20 something, right?
You have about 20 minutes.
About 20, okay, then I accelerate. Then you have this kind of continuity equations. Let's say these are microscopic equations. For instance, these can be written for the microscopic variables, like the density, where you have the sum over all the particles, delta x minus xn. Or in a quantum system, quantum field theory, this can follow, for instance, from Noether theorem. Okay, so these are microscopic continuity equation. Here I'm writing with the at, just to say that in quantum mechanics, these can be, in principle, be operators, okay? This Q and J. And now we want to use this maximal entropy principle. So if we take averages over some state, over a state which is slowly varying, there is a more precise way to do it by looking at the integral form of the equation. But just for illustration purpose, then we take the average over this slowly inhomogeneous state, and we scale the length scale of variations to be very large, so that we look at very weakly inhomogeneous.
So this small l is much, this one, small l is much greater than the capital.
What? The L that appears here is this one.
Yeah, slowly, by slow variation, you are telling that the small l is much greater than the capital. The extent of this also.
I'm saying that this L is large enough so that you see that here you observe a variation over the multipliers only on the scale which is very large. Okay. Small L
It's much better than capital L.
Yeah. This capital L, yeah, maybe I didn't understand. This capital L is the length of this fluid cell here. Okay. And, okay, if you do then take this limit, L to infinity, and you use the maximal entropy, local max entropy principle, then we get essentially something like d in dt okay, where now you see this averages of the density and the currents are evaluated over a local maximalized entropy state of the Gibbs or generalized Gibbs form, so something like the one on the top part of the central blackboard on the specific space-time point, okay? And this is a huge step, passing from the microscopic equation to the macroscopic conservation law. Okay, and yes, please.
So in order to calculate these expectation values, which is some sort of coarse-grained dependence of the conserved quantity, we need local equilibration, but for local equilibration, we need to know how the conserved charge at that particular length scale is.
Yes, exactly. So you need to know what is this expectation value. You have to give a phase, an expression to this over this state.
Yeah, but
You
need to know that a priori. So how can you calculate the expectation value?
Well, this is the expectation value over a state of Gibbs form. So it's given by thermodynamics. So you take the result from thermodynamics and then you upgrade it to space-time dependent. And you have different space-time patches in your system, and how you glue them together, how you connect them to give you connect them using continuity equations. And another point I wanted to make.
So this beta is fixed by local maximization of entropy, right?
Yes, yes. And it's also it's
that also varies with it.
yes, and this space-time dynamics is ruled by this equation. And now, I mean, this might look still abstract. You might believe it or not, but this is exactly equal to that we started from on the lecture. And indeed, I think exercise 1 of the sheet that I have prepared is to show this for the case, simple case of an ideal gas, so without interaction.
Yeah, so there's a self-consistent structure, no? That
Now I tell you. Show that this is. Exactly. Just to say, here I'm writing like this, then in the exercise sheet is written in a more precise form, the statement and the calculation to be done. About the self-organized, the self-structured, we miss an information here, because here we have the average over the current, right? And here we have a density. So we need an equation of state, because we need to fix somehow how the current depends on the density. And this, I think, is the last step that I can do before the end. Is this clear so far, more or less? So take-home message is that Euler equations and viscous fluids are conservation laws at a macroscopic scale when you have weakly inhomogeneous space-time variations, and you can use local maximal entropy principle. This is essentially the summary, few sentences of what we saw. And indeed, as you said, maybe I missed a page. Exactly.
Gabriele, in writing the equation of the local relaxations, we're already assuming the interaction is local in nature, right?
Interactions are, yeah, exactly. Yeah, it's important. Because long range, sometimes you can completely break relaxation, and therefore it's non-trivial whether the limit actually exists at all. In some cases, yes, there are works. Other questions? No? Okay. And then, as you were anticipating, we miss still one bit of information to complete, which we miss an equation of state. Because you see that in the equation, we have this object here. Right? We have the average of the current density on a maximal entropy state, labeled by the parameters beta. Just to say beta, maybe I have never defined, but it's something like this. Okay, it's like a vector if you have multiple of them. Now, multipliers, you see the way they appear in the Gibbs state. Multipliers are introduced to fix, when you do the maximal entropy principle, expectation values of conservation laws, right? So multipliers are in one-to-one correspondence with densities. Okay? So if this object is a function of the beta, then you can also write it equivalently as a function, let's say, J bar of the Q, or the Q, let's say. Okay? So you can see that the current evaluated over a Gibbs state maximal entropy form is determined by the inverse multipliers, or in turn, since the multipliers are in one-to-one with the densities, by the densities themselves, okay? So these two are like two equivalent set of coordinates which label your maximal entropy state, okay? And now we want to see how this object depends on the density, and this is the equation of state. And in particular, if we take that equation above, the framed one, we can write it this way. This one? Yeah, this is an exact statement. It's let's say it's completely generic, and this is essentially a statement about what in thermodynamics you call the equation of state. Right, equation of state tells you it's like the pressure as a function of the density. This is like how the current depends on the density. It's a property of the system. In the exercise 1, for instance, you can write this for the case of the ideal gas to make it concrete. The Q's are the ones, the first part of the equation. Yeah, the Q's, these one are, let's say, let me be consistent with the notation, so I do like this. And are the ones that appear over there. So averages of densities over a Gibbs state, or generalized Gibbs state. So, then if you start from the framed equation, you can do chain rule. Okay, this is just doing the chain rule over there, over the framed equation, and you sum over this index J, which labels the possibly many conservation laws that you have. Just to say, the case of the ideal gas is when you have three conservation laws, right? Number, momentum, and energy. This is a generic case, and this is called multi-component hydrodynamics, when you have these indices which can run over more than one conservation law. And this is just a chain rule applied to that, so nothing fancy. Now we define this object. This is called flux Jacobian. And it's a matrix in the indices I and J. If you want to visualize it as a matrix, this I, you can interpret it as a row index and this J as a column. If you have a discrete set of conservation laws, if you have a continuum, it's different. But it's a matrix, and it's dependent on the densities, okay? And therefore, this we can write it equivalently, like this. Yeah, I just write the equation, and then I turn back and I try to reply. This is an A. Okay, it's this one here. Okay. Yes, you have a question.
The question is that when you write that.
Can you write?
When when you write the first line and when you say that, you know,
This one?
no, this one, equation of state. Equation of state. That So there must be some neglect of fluctuations somewhere.
Okay, very good. Very good. This is related to the viscosity because somehow here we are assuming that the mean of the density depends only, the mean of the current density depends only on the density, right? On the same space-time point. So I'm telling you, the current at the point x and t of space-time is fixed only by the densities at the same space-time point x and t. Of course, this is not completely true, because in principle, when you go beyond maximal entropy maximization, you can have that the density on a point, the current at a point xt depends on, I write it here, something like, could be something like a functional of the densities on x and t, okay, plus something which is like the density, the derivatives of the density. So you don't only look at the point x and t, but also you start looking a bit around it, so to check the space also around it, so the derivative. And this is called the derivative expansion in hydrodynamics. This is the first correction of the derivative expansion, which includes first derivative in space. If you do this updated equation of state, including this kind of fluctuations around the space-time point, and you plug it there, you see you have derivative in x of j, here you have a derivative, then there is a second order derivative appearing. And this coefficient in front has the meaning of diffusion constant, kind of, and this is what brings viscosity and Euler, Navier-Stokes term. This is how you produce Navier-Stokes terms out of this argument, and indeed it's going one step beyond this derivative expansion. Of course, derivative expansion is not at all 100% rigorous, as whether this is in general not convergent, and you stop at the first orders. The first order is the diffusive correction. I think that I have 2 minutes, so probably it's a nice point to stop. Maybe I just show the exercise sheet, and then we can share it. Yeah, for today we stop here, I think, and as I told you, so I plug it again back to the projector, right? It's just to show the tutorial.
Can you just bring it down?
What's the term derivative? This looks like L or U?
What?
What's the term that like
Here?
Yeah, that one.
This is an f. It's a function, let's say it's a function which gives you the equation of state. It's like tells you how the current depends on the density. It's a function that now I am leaving completely generic.
It's a function of Q of X.
Function of yes. And, so just to say this equation here, so the equation of the continuity equation at the macroscopic scale under maximal entropy, this is like equivalent to Euler equations that we started from, and this is the topic of the first exercise. Yes.
This last equation helps you calculating some observable or something.
What is the question, sorry?
This last equation
Uh-huh.
helps you calculating some observable or something.
Exactly. I mean, then you have to specify which density you want. So, for instance, mass, momentum, and this gives you an equation for that observable. It's just 1 minute, and then we go to coffee. Don't worry. We don't starve. I did 90% of what I planned, so I'm pretty satisfied. Typically, it's 50.
So in your teaching, I could see glimpses of Silva and Gambasi.
Huh?
In your teaching, I could see glimpses of Gambasi and Silva.
Of Gambasi, yeah. The stuff with the fraction he was always telling me. When you write an equation that is big, first you write the right-hand side and then the left, otherwise the equal is not aligned with the right, and I get a lot of corrections in my writing, I mean. Yes, exactly. So now this will share it. I think, can we send it by email? Okay. So just today, the topic of today essentially is the number 1, this first exercise, which is about making, no, but now then you get it, so you don't need to take a screen. But just to say, this is to make concrete what we saw and discussed today in general. So instead, we consider a classical gas, let's say, with 3 conservation laws, equation 2, momentum, particle, and energy, described by a grand canonical equation 3 and 4 probability measure, Gibbs. And then we want to show that essentially when you start from microscopic conservation laws, equation 6, and you use the maximal entropy principle, you can rewrite the equations that we wrote today at the blackboard, the equation of the continuity equation macroscopic scale in the form 9, 11, which are Euler equations. We do this in the case of the ideal gas, which is of course treatable in an analytic case in a relatively simple way, so that we can see this directly from a calculation and hopefully becomes clearer. Point number 4, I didn't discuss the 10% that remained out to today. If we do it for the moment, don't look at it. Maybe we discuss it in the afternoon in the other lecture. And then the other exercises will follow the next lectures. So at the moment is number 1.
Can you suggest a good reference?
Here I have put a couple. For instance, Spawn is the book that I was starting from, which discusses this local maximal entropy principle. It's chapters 1, 2, and 3, essentially, where you find a lot of discussion about this, also in a mathematically more rigorous way. And then there are these lecture notes from Doyon, where there are also discussions about these topics. The number 2 is more pedagogical, I would say, because Spawn is very rigorous mathematically, goes deep. In the lecture notes, Ben tried to be more pedagogical. What? Maybe yes, but I have not read that.
Okay, so if there are no questions, let us thank Gabriele.